Hello everyone! Today we will be looking at a parallax interior shader leveraged for cities, for Houdini and Redshift. This technique allows us to control the lights for an entire city while maintaining close-up fidelity in a single material. And with that, let's get started. First, let's talk about how the shader works. Now, if you saw my Octane tutorial, it works about the same, albeit with a few less features. While the scripts are different, the underlying calculations are about the same. This version was last modified by Saul Espinosa. I further took that and just exposed the parameters of the shader so we can then use them with attributes. But otherwise, it's the same that you get from the repository. Let's demo how to get a single window working before we move on to the city. So let's go into our geometry context. Grids by default in Houdini will face Z negative, and to get this to work, we need that to be Z positive. That's very important. So we reverse that. We set up our UV unwrap to stretch with 0 spacing, set our material, add a normal, and pack it, exposing our attributes. Next, we head over to our geo context into our Redshift object tab. Go to instancing and make sure we enable instance SOP level packed primitives. This is important for instancing. The shader will not work without this. Okay, now that we have our geometry set up, let's head over to our material content. Now let's open up the shader. We see our OSL script node over here with all of these parameters. So let's open up the IPR and see what we're working with. And already we have our window interior. Now, color correct and color clamp are pretty self-explanatory. I'll skip that. Flip, flop. You flip it, you flop it. Now our window shape. These are the parameters that really make a difference. So window aspect, you want to match the aspect ratio of our shape. So in this case, it's a perfect square, so we set it to 1. Different values will give us very strange results. Room depth is just how deep our room is. Set that to 1. And then our midground will control our midground element. Of course, we can offset that as well, which is pretty nifty. Foreground enables or disables our curtains, and we have a few extra components here. Now, I often like to add a color correction node and bump up the level a bit. It tends to get quite dark otherwise, I've found. That's all there really is to it, to the basic shader. The real fun is when we start leveraging attributes to apply this at scale. Moving on now to the city. Before we can jump into the shader, we need to prepare each building in a very particular way. Thankfully, this can be pretty much automated, where you could easily create an HDA out of this. For now, I just use subnets. I'm going to jump into my favorite building out of the bunch, building 50. If we close this real quick. In the Octane version, I showed you how to set up your windows using a building built for the purpose. However, most of the time, you won't have the time or even desire to model your own building, so you have to take what you get, and that can cause a lot of complications. This is one way to automate the process to prepare your windows. So we have our building. I split it based off the window glass material it came with. I run a quick group and blast just to select the windows we want to use. Then we jump into our subnet. Now at the top of the subnet, we do some basic processing, removing attributes, deleting small parts, adding a normal, doing a fuse and dissolve. Not necessary for this particular model, but it's very helpful for other ones. We run a connectivity for a primitive class attribute. I guess add a normal again for some reason. promote the class to points, and then we run a extract centroid. This will come in handy further down the chain. Now, one of the two reasons we want mops for this, mops and mops plus is required for this to work, so make sure you have a license for mops plus. We use the mops noise falloff nodes to create patterns for our attributes. To make this easier to see, let's change our background to dark and remove the grid. And let's go ahead and drop down to the last one. You can see all of our point attributes using depth, emission, several different noise variations. T noise is the noise we will use to drive our transition between day to night. F noise is what we use for the floor emission for each window. We go ahead and convert that mostly to integers using this wrangle, though I did decide to keep the depth level a float. We add an ID attribute using the point number. Then we copy them back to the geometry using this naming convention here. Floor noise, transition noise, emission level, etc. Now, this is great, but the tricky thing is we need to get all of these windows to world 0. Otherwise, the shader and other properties will not work. So, let's turn our grid back on. Using some handy math from Ben Carmelli, we set up these matrix attributes. And then using that, we wrangle that down to world 0. This way, no matter the size or scope of the window, our parallax will always look correct. We run this calc aspect wrangle here, and we get this aspect float. Delete attributes we don't need. Now, we could pack it as is, as fragments, and run it just fine. Problem is, that gets incredibly heavy when we're talking about a city. Early testing showed it would take up to 5 minutes to load it to the IPR. So instead, we're going to instance a single window and stretch and skew it post-packing to get it to match the scale of the windows we need. For obvious reasons, this only works on flat grid windows. Square, rectangular, you get it. Curved geometry does not work with this setup. To do this, we set up a window as we did in the demo. Then we run a wrangle. I believe we're running class. Yes, we're running class. So we go ahead, promote our aspect attribute, transfer the attributes over to our new packed window, use a match size, but not scale Z, importantly, otherwise the parallax will not work. It will just collapse it down. Then to move the windows to their original position, we reference that extract centroid from earlier, grabbing just the point we need, and copying our window to that point. If we run the full for each, we'll have 5,000 windows with unique aspect ratios based off of a single instance. Next, we add a flip randomize. I should really call it a flop randomize because we're not randomizing the flip. Now, the second reason we need mops, and the reason why we need mops plus, not just mops, is our attribute mapper. Now, in Octane, this does not work. That was my first approach. For whatever reason, Octane cannot handle string attributes for textures. That's why I developed the UDIM solve for that instead. UDIM is more efficient, but it's pretty annoying to manage. So instead, using the attribute mapper, we are able to create a texture string attribute and just drop in effectively as many textures as we want. In this example, I'm using 20 for the night and 20 for the day. Next, we go to our mops assign mapper. I'm using a random match method. I made sure to match the random seed for both the night and the day. And I am mapping the texture to a text night and text day attribute. And as you see, we have a total of about 21 point and primitive attributes that we will be sending on to our shader. And that's how we prepare our windows. Pulling out of the subnet, we will combine it with the rest of the building. The facade, I add a override material, delete some attributes, pack that, and we are off to the races. One final note before we move on to the shader is how we're doing our city-based scattering. Now, this is a dead simple distribution. Here we grab all of our hero buildings, transform them as needed, and create names for them. We do not want to pack the buildings again because packing the packed windows will break the shader. We come down here, merge them together, add another transform. For the point grid, it's pretty simple. Add a grid, reduce it down to points, add a mops randomize for random orientation, and then very importantly, we add one more attribute, a building index. And this will allow us to address different buildings as a whole randomly in addition to our windows. Finally, we run a attribute from pieces using our name piece attribute. We're just doing a random mode here. And then do a simple copy to points using our name. And there we have it. And again, we really want to make sure we're not packing them again. We only want our windows to be packed. We still need that exposed for Redshift. In testing, I have seen over 5 million windows load with no problems. And finally, in our manual scatter, we go to our Redshift object tab, instancing, and apply our instance top level packed primitives. And for prep, that's it. Now, moving to the shader. All right, this looks like quite a bit. I'll load up the IPR and then we'll start reviewing what exactly we're doing here. So let's go ahead and reload this. And as you see, this only takes a few seconds to load and we're already rendering. So at the center, we have our night and our day OSL nodes, identical to the demo. We're reducing the saturation a little bit because we're doing some post color operations, and we'll get to that in a bit as well. As you see, this is where we're pulling in our night and day string attributes, along with our flip integer and our aspect ratio float. And we're plugging these in accordingly. This was the main difference between the original script and my version. Pulling back a bit, we're going to go from left to right to review what exactly we're doing here. So, in the back, we're pulling in our window emission attributes, our floor noise. This will determine which floors are lit and which ones are not. Really, we'll just be switching between our day and our night textures. You can use as many or as few attributes as you like. The more the merrier, and the more variation you'll get. So I am using a randomized color switch to dial in the ratio of how I'm addressing the integers. And keep in mind we have our input ID mode set to user data ID. Over here, we're pulling in our building index to determine which building gets which texture pattern. And if we go through our seed, you'll see this updates pretty much instantly. And you can already see what kind of variation we can get. Up here, we're adding in random windows that are illuminated from day to night. This is a good way to add a little bit more variation, a little bit more randomness on top of our patterns. So we're pulling in our window ID attribute to create, again, 4 variations to pull from. Once again, we are using our building index to randomize which building gets which variation. You'll see for quite a few of these that I'll have shader input number 4 blacked out with 0 weight. That's a bug I've seen. I've already reported it, where on the 4th or 9th shader input, it will sometimes disconnect when you reload the HIP file. I don't know why. It just does it. So I'm just kind of bypassing that channel. As you see, we are adding that window randomization to our pattern. So our pattern window switch and our random window switch. Next, we are using a day to night transition to mix between black effectively and these window patterns. So to do that, we have our transition noises. This time I have 4 of them. Again, as few or as many as you'd like. And I'm actually animating these parameters here from 1 to 0. And I actually have the black weight just mirroring the original animation. And as you see, I have these keyframed down here. And if I were to scrub the timeline, get this to load up again, you will actually see that in action. Let's pull it up here. There we go. Once again, we're pulling our building ID over here, and we're randomizing between these 4 weights. So that's it for the day to night mask. That's all what these nodes are for back here. We then pump that into our user data to switch between our 2 OSL nodes. And for the diffuse channel, that's about it. We are bumping the level scale up just a tad, up to 5. However, for emission, it gets a bit more tricky. This mask range here is converting our integer to float. We're going to use this to ensure our daylight textures are not emissive, so only our night textures are giving off light. We'll review this composite in a minute. Now, down here is how we set the colors. This is why we reduce our saturation a little bit, because we're going to be doing some color operations to add to this city-wide shader. Over here, we have all of our color profiles that we're going to be randomly applying to each building. I believe we have 6 of them, from pretty warm to pretty cool. And you can see which kind of colors we're applying. I'm also adding one that's just random colors entirely that you can play with the weight of. Once again, another building index, and we could randomize the application here. Or change the weight. For this demo, I wanted it to be pretty cool for contrast. Now, as part of our compositing, we're actually going to run a color key. A color key OSL script from the same repository as the Parallax script. we're setting this to grab the brightest values from our texture that we're going to use to mix between the light and the dark colors for the most natural composite. We add a darken color correct node here, reducing our saturation a little bit and darkening our level. Add a color mix. Then we do a hard light on top of our original textures. For this demo, I wanted a bit more of a contrasty saturated look, so I actually pumped up the saturation a little bit. So you can actually see what they originally look like. Wanted to pump that up a little bit. Not that much. All right, we then wire this up all the way up here. We are multiplying to this window mask here. So these colors will only be applied to our night emissive textures. We add one more layer of variation. This is using one of our noise attributes, our emission level. We use that to drive between these different colors that are going to be multiplied onto our emission. Since Redshift doesn't really allow you to directly address the emission intensity, this is kind of a way to hack that. The emission level on the shader is set to, it's pretty high, it's set to 100. That's so we can subtract that emission through the shader using this method. So we can, again, change the seed, let it load for a moment, and you can see how dramatically that changes the look. And I wanted a bit more of a sparse window look for this scene, so we can like really exaggerate that, or we could really reduce that down and have it be a bit more, you know, Times Square overwhelming. No problem. Just reset that. All right. We then apply this subtraction via multiply. And then we add a little bit of daylight emission, just a tad, a very little bit, so we can see it a bit better in a night application. And that's really about it. After that, in our standard material, we have our emission set to 100. We are adding a bit of coat with a high IOR, some roughness. This way we don't need to add a reflective glass pane in front of the shader. It's a bit more optimized this way. No reflection needed. That's the shader. As you can see, you can make it as simple or as complex as you like, but this scales really well. I've done this with thousands of buildings and it doesn't break a sweat. Unlike the Octane version, this script doesn't allow you to disable left or right walls, which would allow you to see through corners like you can in the Octane version that I have. However, at this scale, for most of these buildings, it's really a non-issue. I will supply a simplified version of the scene with my own models on the Gumroad for free. Please let me know if you have any questions or run into any problems. I'm more than happy to help in the comments, and I'll see you next time.